Yeah, so as you know, machine learning methods have become omnipresent in many geoscience fields. In particular, they are used to spatially predict a target variable when auxiliary information is available everywhere within the study area. Although machine learning methods like random forest or supervector machine or boosting show competitive prediction performance, they do not exactly match the target variable at sampling locations. On the other side, competitive geostatistical techniques like regression kriging can perfectly match the target variables observed value at sampling location by construction. And in many geoscience applications, like in mining geology, it's often very important to try to match the observed value of the target variable at sampling location. And especially when the target variable's observed value can be considered error-free. Here you have a map. Here you have a prediction map provided by random forest. The target variable here is categorical. We have 5 categories. Random forest is a very popular machine learning method in geosciences. It's well known for its ability to handle a large number of predictor variables and also for its ability to capture very complex nonlinear relationship between the target variables and the auxiliary variables, and also it's a non-parametric method. And here you have the predicted category at the sampling data locations. And here you have the observed category. So this is the data. So if you see these two figures, you can clearly see that there's a disagreement between the predicted category and the observed category at some sampling locations. And in this case here, the random forest provided a misclassification error on the training set of 33%, which is very high. So in this talk, I'm going to show you a new random forest-based approach, which ensures that the target variables is exactly conditioning to the data, meaning that the misclassification training error is 0. The rest of my talk will follow this plan. So I will describe the different ingredients that constitute the proposed method, and then I will illustrate the proposed method on a real-world data set. And finally, I will provide some concluding remarks. So we consider here a categorical target variable, C, defined over a spatial domain of interest, D. The categorical target variable has K categories, which are mutually exclusive and exhaustive. And the categorical target variable here is measured at N sampling locations. In addition, we assume that we have a set of P predictor variables that are exhaustively known over the spatial domain D. And the goal here is to try to predict the target variable C over the domain of interest D, here represented by N grid location, such that the predicted categories at the sampling location exactly match the observed category at sampling locations. So the starting point of this proposed approach is the traditional random forest classifier. So the random forest classifier is just an ensemble method where several individual decision trees are trained of different subset of the data using different subset of the predictor variables and followed by an aggregation, which could be, for example, here, the majority vote. So the starting point of our proposed approach is to consider this ensemble of decision tree. So B here is a number of decision tree, and each decision tree here, we will call that a tree predictor. So this will be, for example, the prediction over the spatial domain interest D. So because at this stage, this tree predictor doesn't necessarily match the data, we are going to call them unconditional. So we assume that we have this ensemble of unconditional tree predictors. And the idea of the proposed approach is to try to use this ensemble of unconditional tree predictors to generate an ensemble of conditional tree predictors. How to do that? As you probably see here, this ensemble of tree predictors here are categorical. So the next step, we will try first to transform this unconditional tree predictor, which are categorical, into continuous quantity using the sign distance. So if you have a category, ck, right? So we can represent this category using a sign distance function, pk defined like this. So what does that mean? Here, for example, we have a map with two categories, 1 and 0. Here you have the sign distance associated with the category 1, and here you have the sign distance associated to the category 0, which is just the opposite of this one. So the sign distance is what? It's just a distance to the closest point of the opposite category. So imagine that we like to compute the sign distance associated at the category 1 at this specific location here. It will be the distance to this point here, which is the point that has the opposite category. And because here we observe the category 1, the sign distance will be negative. So that's why we have this value here. Now, for example, if we are here and we would like to compute the sign distance associated again to the category 1 at this location, it will be probably this distance from the closest point of the opposite side. And now, because here we don't observe the category 1 but the category 0, the sign distance is positive. So this is how, given a categorical data, we can transform that into sign distance, which is continuous. So in this step, giving the ensemble of unconditional tree predictor, we're going to transform them and an ensemble of sign distance function for each category. So if you have k categories, you're going to have k ensemble of sign distance, each ensemble representing one category. Now, the next step is to try to perform the principal component analysis on each ensemble of unconditional sign distance functions. And we get this decomposition where each sign distance function could be written as a linear combination of some PC score or coefficient and this PC factor or eigenfunction. So in practice, for each category, the PCA is applied to a matrix gamma K. This matrix has B row, B being the number of decision tree, and N is the number of grid locations. And each row here represents a single unconditional sign distance function. So at this stage, since the ensemble of unconditional tree predictor are not exactly conditional data, so also this sign distance here is still unconditional. So the next step that we're going to do here is to try to find now a new PC score that will help us to exactly match the data. So how we do that? So now we define this sign distance where this coefficient here are random and unknown, and this is the eigenfactor, this is the PCA factor that we compute previously. So now what we like to do is to try to generate new principal component score such that we are able to match the sign distance. We're able to match the data. So now, what does that mean by matching the data exactly? That is very simple. The value of the target variable at each sample location will inform the sign of the sign distance function associated with any category. So imagine that at location X1, we observe the category 2. This means that the sign distance associated with the category 2 at location X1 is negative, and the sign distance associated with other categories at location S1 is positive. So this is how we translate the observed value of the target variable in terms of an inequality in the sign distance. So now for each category, the conditioning to all the data locations could be expressed like this as a system of inequalities, where these coefficients are the unknown and these values are fixed. This is just the I, the PC factor. So we can summarize this system of inequality in this matrix form. Now, given that we were able to transform or to translate the exact conditioning into a system of inequality, now we are going to see how we generate exactly these coefficients. So in order to generate the new PC score that match the data, we are going to solve this quadratic minimization problem. So here, your unknown here is the theta, the coefficient I would like to generate. And here you have beta k is a vector that we assume that it follows a normal distribution with the mean and covariance given by the unconditional PC score. So this is the average of the unconditional PC score, and this is the covariance matrix of the unconditional PC score. So it means that for each sample beta tk here, we are going to use the quadratic programming to generate a theta t that minimize this quadratic form and also satisfy these inequalities constraints. And this is how we are going to generate the PC score that match the data. Now, given that conditional PC score, the next step will be try to compute now the conditional sign distance. And this is done simply by reconstruction. So now we are able to generate the conditional PC score. So we combine them with the previous PC factor. And by doing this, these sign distance function here are exactly conditioned into the data. Now, the next step will be to try to apply a truncation rule to obtain the conditional tree predictor. And the truncation rule here is very simple, is that at each location, you are going to choose the category that gives you the smallest sign distance. And now, given this ensemble of conditional tree predictors, you can now apply a majority vote rule to get your predicted value over the spatial domain of interest. So here, just to summarize here the method. So the first step, you apply the traditional random forest on your data. And the outcome here is an ensemble of unconditional tree predictors. The second step, you transform this ensemble of unconditional tree predictors, which are categorical, into an ensemble of unconditional sign distance functions, which are continuous. And then the third step is that you apply the PCA on each ensemble of unconditional sign distance function. And the outcomes here are the unconditional PC score and the PC factor for each category. And the fourth step is to generate a new PC score that exactly match data using the randomized quadratic programming. And when you get that, you can easily derive the conditional sign distance by reconstruction. And the sixth step will be just to turn out these conditional sign distance functions into conditional tree predictors. And the last step, you just apply the majority vote rule to get your final result. Okay. Now, I'm going to show you an example. So here, the application example is, so the target variable here is the thallium geochemical configuration that has been transformed into 5 categories, so 4 quantiles, and we have about 568 data locations. So in terms of predictor variables, we have 26 predictor variables that include the elevation, the gravity, the Mach, some land stat. So the data have been divided in 2 parts, the training set and the test set. The training set has been used to train the machine learning model, and the test set is used to assess the predictive performance. So here, this is some example of the predictor variables. So this is the elevations. This is the this is the Booga anomaly. This is the potential counts. And now this is the training data. And here now you have the in black here is the training data, and in red is the testing data. So for this case study, we apply first the traditional random forest, so using 10,000 decision trees. So in black one here, this is the unconditional PC score. So we have 10,000 unconditional PC score. And then now in terms of the conditional PC score, we generate 1,000. So, so that is the what you observe here in red. So you can see that the cloud of conditional PC score is less scattered than the one of non-conditional PC score, which makes sense because of the exact conditioning. So we try to reduce the space. Now, in here you have the prediction map for different methods. So this is the regression kriging of indicator, which combines the logistic regressions and the kriging of the residuals. So it means that you first apply the logistic regressions, and then now you try to create the residual and you add back to the regression estimates. Here you have the classical random forest, and here you have the proposed method, and this is the training data. So about the regression kriging of indicator, you can see that the map here is a little bit noisy, and it makes sense because in this case here, the residual has almost no spatial structure. So this is the residual that we have from the regression kriging of indicator. So there's almost no spatial structure. So by clicking the residual here, it's more like you're adding the noise. So that tells us also that in this case, I mean, try to conditioning by the residual is not necessarily the best idea when your residual don't show any spatial structure. So, and here, so from the proposed approach, we can clearly see that it perfectly conditioning the data, right? Compared to the classical one, which has a miscalculation error of 33%. And here we don't have this kind of noisy map that we get from result kriging of indicator. Now, we are also able to compute the prediction alternative map based on the entropy. So this is the one obtained by the regression kriging of indicator, it's a bit noisy. This is the one by the classical random forest, and that's the one with the proposed approach. So we can see that when you compare the two maps, that here the uncertainty is reduced. That makes sense because now we try to exactly match data. And also we can see, for example, in this area where you have low uncertainty, because in this area it's locally mostly dominated by one category. So normally in area where, or in local area where we only have one category, the uncertainty is tend to be very small. So that's, you have these kind of things in this different area here. Now, let's see what are the predictive performance statistics in the testing data. So this is the result that we get here. This is the misclassification error, and this is one the run index. So you can see that the proposed method gives here a very low misclassification error compared to classical traditional random forest and to regression picking of indicator. In terms of randomness, it gives the highest value. So from this example, we can notice that this method is able first to provide exact condition and predictive map, but also is able to provide a predictive performance that is higher than classical methods. So here I would like to highlight some remarks about this approach. It has some attractive features. The first thing is that it's very easy to implement since it's combined some well-known tools that we're using usually. So like sign distance function, classical random forest, and qualitative programming. And this method has the advantage to easily handle a large number of categories through the use of the sign distance representation. Because as you can notice here, you can perform everything in parallel given the number of categories. And it also has the advantage of non-producing noisy map, like the regression quick of indicator, which is very important. And something also very useful with this method is that the predicted probability by construction is between 0 and 1, and is sum up to 1. But in the regression picking of indicator, it's not the case. We need to do a kind of post-processing to have this constraint. Another feature of the proposed approach is that the updating of the target variable can be done very quickly when you add few observations. So when you add few observations here, you don't need to run all the process from the beginning to the end. You can only run the randomized quadratic part, because adding new data means you add new inequality constraint. So if you just add new few observation, you could just run the last part. But of course, if you add a large number of observations, you need to run everything from the beginning. Now, it's very important here to mention that the proposed approach requires that the number of unconditional tree predictors should be very large. So the number of tree that you are using when you perform the traditional random forest should be very large for the reason that you can see that the number of data, the number of observations here define the number of constraints. So if you have a large number of data and we just take a few number of constraints, what's happening is that you are not able to explore very well the solution space. And also you can have very small uncertainty. So it's very important to make sure that you take a very large number of unconditional tree predictor. But the good thing is that this parameter is a free parameter in a random forest. So we are not really limited to choosing a very large number. Another thing here is that in this approach, we are using the random forest, but with this approach, you can use any type of answer method, as long as you are able to have a method that is able to generate an ensemble of models. You can use that to perform the exact conditioning. Now, we also have a similar approach for the prediction of continuous variable, because what you saw here is when you like to predict a category of target variables. But when the target variable is continuous, we can use a similar approach. And we have published this paper where we show that. The idea is very simple. Now, because the target variable is continuous, you are going to use the regression random forest. So again, you are going to have an ensemble of unconditional tree predictors. Now that we would like to match exactly to the data. But here, the difference is that matching data here will be equivalent to have a system of equalities. And if you assume that your PC score follow a kind of normal distribution, in this case, you can directly have the closed form of the conditional PC score, which also will follow a normal distribution with some specified mean and covariance. And then you can easily sample this new BC score that we exactly match the data. So that's all I would like to share with you today. Thank you so much for your attention. I'll be happy to answer your questions.
Thank you very much, Francky, for a very interesting talk. There is a question from Guillaume Pirot. Guillaume, would you like to ask your question? Not possible. Okay, I'll ask
Frankie.
it for you. Yeah, okay, good.
Yeah, no, a very nice presentation. Thank you, Frankie. I was wondering, when you show the classification error in your application, the improvement, is it mainly due because you include perfect conditioning? Or have you also tried to compute this classification error just outside the conditioning locations?
Yes, we did that. This is the that's what we show here, right? This is the miscalculation error on the testing data, right? So we can see that the proposed approach gives a better result compared to the classical random forest and the regression kriging.
Okay, thank you.
Any other questions for Francky? Gerald.
Thank you for that interesting talk. I understood very clearly how the method works, or at least I hope I will remember afterwards. But my question is somehow the whys. So why did you construct it in that way? What motivated you? And why does it show so good results? So have you any idea what the mechanism is that makes that prediction so good?
Yes, thank you so much for this interesting question. So why is it motivating? What is the motivation of that? The thing is that, as a geostatistician, first we are very familiar with the exact conditioning. For us, it's very normal, right? In kriging is exact conditioning, conditional simulation, exact conditioning. And in practice, when, for example, you work in mining geology, they would like to have a model that exactly match what they observe. So now the thing is, we know that classical method like regression kriging doesn't give sometimes very good results. So now the idea was, how can we develop a machine learning model that has the same properties like geostatistical model? So that was the first idea. Now to do that, we have this idea of exactly in geostatistics we have a kind of unconditional simulations that we are using to try to turn in conditional simulations. So this is the same idea. So we know that at the beginning, we apply the classical machine learning like random forest that provide us a kind of unconditional simulation, I will say like this. And then now the idea is, how do you turn out this in terms of conditional simulations? Now, why we have this good result? This good result is because if in your data you have a kind of good spatial correlations, right? By exact conditioning, right, you expect also to improve locally the prediction. Okay. So for example, imagine that you are here. When you do the exact conditioning, if this area is mostly dominated by the same category, because of doing the exact conditioning, you also improve in somehow the prediction. Is that answer your question?
Yes, thank you.
Thank you so much.
Do we have any other questions for Francky? Hang on.
It's actually not a question, but we have tried with other efficient methods like iterated watersheds power spectral clustering and watersheds for classification. Probably Dr. Francky can have a look at them, and they also have yielded wonderful results on the spatial data.
All right.
Mostly we tried on, mostly that hyperspectral remote sensing data we have tried. You can just have a look at it. This is just for additional references. Thank you for your excellent talk.
Thank you so much.
Well, thank you very much. And I would like to thank Francky again for his talk. We are now at our last presentation of the evening, and this presentation will be